So last hour, so bear with me. And actually, I will not be talking about learning and weight spaces. So I will talk also about learning and weight spaces, but probably wanted to say more general words about, well, basically about science, not only about machine learning and artificial intelligence, and maybe some lessons and a little bit of long summary of what we've been seeing in these days and how the community is developing and how where these methods are actually useful and what likely will be happening next in this field. So allow me maybe to start with, so I like starting with quotes. So I would like to start with this quote, and imagine that you travel long distance to meet your scientific hero, right? I presume everybody here has their heroes, and unknown to you, instead of a life scientist that you're expecting to meet, the devil has taken his place. And you ask questions to this presumable scientist about what life is, right, and what science is, and he responds to you in this way. And here I quote in translation, who traces life and seeks to give descriptions of the things that live, begins with killing to dissect. He gets the pieces to inspect, the lifeless limbs beneath his knife, all parts but link which gave them life. So I don't know if you're familiar with classical European German literature, you would immediately recognize the scene from Faust. So Goethe's masterpiece, so this is where Mephistopheles talks to a scholar from the first book of Faust. And I think here Goethe describes poetically but very accurately the problem that we encounter in biology in particular, but I would say in general in sciences. So it's the problem of scales, right? So if you take a living organism, you can look at it either at the very low scale, right? So individual molecules and atoms that comprise them, all the way to cells, right? So the basic building block of a living organism that then form tissues, and then they form organs, and then they form entire organisms and entire ecosystems. So these things live at very different scales, both temporal scales and spatial scales, right? So if you talk about molecules, we are talking about nanometers and femtoseconds. So that's how they work and how they interact. If we go to ecosystems, we are talking about things that span potentially miles and can live for hundreds of years, right? So we have probably something like 15 orders of magnitude of a gap. Now, the problem is why this is a big issue in in science in general, in particular in life sciences, is that at the very low scales, we understand everything, right? So we have a very exact, very accurate, very precise description of how things work, right? So we know exactly how atoms and particles work. But as we go to the higher scales, we have no idea, right? We don't have an equation of a cell. And also the fact that we know how things work doesn't mean that these are tractable problems, right? So let me give you a specific example. So not in order not to make this kind of hand-waving discussions. So let's say that you want to simulate an atom, right? So you probably, everybody here studied physics, right? So you're familiar with quantum mechanics. So take what is the first atom in the periodic table, right? So you take the atom of hydrogen. So it has just one electron, right? So what would be the solution of a quantum mechanical equation for this particle, right? So we know this is the Schrödinger equation. It looks like this, right? So we have the Hamiltonian, we have the potential, and psi here denotes the wave function, right? So that's how quantum mechanics describes the behavior of particles, right? So how do we solve this equation? Of course, we cannot solve it in closed form, so we need to solve it with numerical discretization. So let's take a grid in 3D space, right? Let's divide our cube where this atom lives into, let's say, 100 by 100 by 100, right? So this is very coarse grid for any practical purpose, right? So we have n equals to 100. What's the number of equations, right? So the positions of the electron is x, y, z coordinates. Each of them can be 100, right? So 100 to the power 3, right? So it's 10 to the power 6, right? So 1 million linear equations, right? Not a big deal, probably. Even on this computer, it will probably take something like a gigaflop, so I can solve it in less than a second, right? So on this laptop. So not an issue, right? So sounds like an easy problem. So I will need to some matrix inversion, right? Or whatever method you like for solving equations, okay? So what goes next after hydrogen in the periodic table? helium, right? So what is the situation with helium? So helium has 2 electrons, right? So for each electron, again, we have x, y, z coordinates. So we have now 6 degrees of freedom, right? So for each of these positions, 100 possible, 100 by 100 by 100 possibilities, right? So in total, n to the power 6. So this is already 10 to the power 12, right? That's the number of linear equations. Again, the complexity, if we want to solve it on a computer, 10 to 16 flops, right? So this already will take about 4 months to solve this, right? Now, you can see already how the complexity grows. So it doesn't grow linearly. It's not just like increase the number of electrons by 2 and the complexity grow by 2, right? So it's a difference between something that is tractable and untractable. And this is just one atom with 2 electrons. So if you take a small molecule drug, so something like paracetamol, it will have probably 20 atoms, about 80 electrons. And I can assure you that it is absolutely impossible to solve this system of equations on a computer, on any computer. Take all the computers in the world and wait for the entire age of the universe, you will still be crunching numbers. So nobody even tries. So it's totally intractable. Therefore, you need, so even though in principle you have exact description of how things work, these problems are dimensionality cursed. So these are multi-body problems. You cannot solve these equations. So you need to move to a different level of abstraction. What's the level of abstraction that quantum chemists, for example, use? So you replace wave functions with probability distributions. So this is what is called density functional theory, and Nobel Prize was given for it in the 90s. So this is how you simulate molecules. But even if you go to a slightly bigger molecule, right? So a protein, about 10,000 atoms on average. So this already wouldn't work for a protein, right? So this is still too high complexity. So you need to abandon altogether the quantum mechanical models. So you need to go to classical models, what is called molecular dynamics. Again, the Nobel Prize was given about 10 years ago to Michael Levitt and others for development of these methods. So basically, as you go to bigger systems, you need to throw out some details, and at some point you ask the question, am I solving the right problem? So I assumed so much, I approximated so much to make the problem tractable that maybe I completely threw out all the important details, right? And this is just one protein. So in a cell, we'll have something like 10 trillion atoms, and we have trillions of these cells, right? And look at this mess, right? So this is just one part of a cell. So it's, all these little balls are atoms. Look at how complicated it is, right? So we cannot really, even if we know the basic principles, how these things work, we absolutely cannot solve them, right? And I like Philip Anderson, so I quoted him in the first lecture. So he was writing in the same article, so it's actually a beautiful essay in Science in 1972. It's called More is Different. So he was saying that the ability to reduce everything to simple fundamental laws doesn't imply the ability to start from these laws and reconstruct the universe. Instead, at each level of complexity, entirely new properties appear. Right? So he was talking about emergent phenomena, the idea that, for example, why physics works, right? Why chemistry works. So haven't you ever been surprised why chemistry, basically the underlying of principles of it are quantum mechanics. And yet when chemists talk about chemical reactions, they don't solve quantum mechanical equations. So it's some sort of calculus, right? So in most cases, you can completely forget about quantum mechanics. You don't need it for chemistry, right? So why? Because there is this emergent phenomenon, right? So you have a different level of abstraction and different description for phenomena that happen at certain scales, right? So statistical mechanics, thermodynamics, the fact that you have quadrillions of particles that move in this room, right? But the only thing that you need to know to simulate gas in volume is temperature and pressure is quite remarkable, isn't it? Right? So, but not all physical systems are like this, and at certain complexities, we have not discovered the laws that govern these systems, right? And that's exactly what Anderson is talking about. Now, I already mentioned this difference between software 1 and software 2. So in software 1, you need to start with the logic that describes your system, right? So whether it's a differential equation that governs your simulation, then you apply it to data, you do number crunching for maybe a few seconds or a few days or a few weeks, depending on the complexity, you get the answer. What happens when you start in a situation when you don't have the equation that governs your system, right? Like in biological sciences, you don't have an equation of a cell. So what would you do? So you need to replace the order, right? So that's why you need to resort to machine learning, and that's why it's widely believed that machine learning is probably the only potentially solution for these kind of problems, because you don't have a good approximation or a good model of the system. You might know something, so right, it might not be a completely black box, but this is how you work, and this is why deep learning has been successful, right? So we talked about deep learning at length, right? And we had this example of cats and dogs, and basically considering as a glorified curve fitting, and then what kind of assumptions can you make, right? So all these 2 days were exactly what goes inside this black box, how to make it not dimensionality cursed, right? So how to avoid the curse of dimensionality, the fact that the number of samples that you will need to show, right, the size of your training set will depend exponentially on the dimension, right? And the way in convolutional neural networks, for example, as opposed to multi-layer perceptrons, was to have these layers that do not have a quadratic number of degrees of freedom, but to have it controllable, right? So if I connect an output neuron only to my neighbors, right? So I have some local connectivity in the neural network, and then I share the parameters, right? So these two principles, locality and parameter sharing, actually reduce the number of degrees of freedom just to order of 1, right? So these are the convolutional filters that we see in convolutional neural networks, right? And also the property that we get is also translation invariance, or more correctly equivariance, as we've seen today in the lecture about convolutions. And this is important in pattern recognition problems. For example, when you want to detect objects in an image, no matter where they are located, right? So you want shift invariance. Now, what people have been doing instead, trying to build equations of a cat, right? So we again talked about it in the first lecture. So the typical computer vision pipeline was to extract some kind of features, handcrafted features from the image, and then aggregate them in some way using, for example, histogram. And this has been the standard method in computer vision for more than a decade, until 2012, where this breakthrough happened with convolutional neural networks. Enough data and enough compute allowed to train sufficiently powerful convolutional neural networks. So everything since 2012 has become based on deep neural networks, right? So some cynical people talk about the BDE, the before deep learning era, right? So like we have the B before the common era and after the common era, right? So year 0, so that was 2012 was the year 0 for this community, and many other fields have transformed in this way. And again, it was a triumph of deep learning, and many prizes were distributed. So you could, if you think of it, it was kind of a lesson, right? And this is, here I'm quoting from Richard Sutton, so he himself got the Turing Award last year. So he called this the bitter lesson, and the idea that simple systems that scale with available computational power will eventually outperform more complex systems relying on human knowledge, right? So all these methods building equations of cats were based on human knowledge, handcrafted descriptors, as opposed to just harnessing the compute power. So more GPUs, more data, training for a longer time, eventually beats the handcrafted, the human intuition-based approaches. And indeed, the entire business of the first $5 trillion company, NVIDIA, is based on scaling laws, right? So they have understood this idea. They are building GPUs that are increasingly more powerful. And as you probably have seen, it's not a single scaling law, there are multiple, right? So the first AI models were talking about pre-training scaling, then post-training scaling, and nowadays we have test time scaling, or the inference time scaling, right? So all the chain of thought methods and so on, right? So this is Jensen Huang, the CEO of NVIDIA here. So we also saw, we talked about applications of graph neural networks, right? So the classical problem in virtual drug screening. So when you have a molecule represented as a graph and you want to predict its properties. So here we have different type of priors. So here we need to assume permutation invariance, right? So saying how the atoms are ordered in the molecule doesn't matter. And again, graph neural networks, about which you heard extensively mostly yesterday, they also implement this principle of locality and shared parameters, right? So what is locality? Meaning that each node receives messages from its neighbors, right? So you don't get information from all the graph, you get information only from your local neighbors, and shared parameters meaning that the way that you aggregate is the same everywhere, right? So the features themselves, the structure of the graph locally might differ, but the aggregation rule itself is the same, right? So it's repeated, and therefore you can apply it to a graph of any size, potentially, right? And again, we've seen that this is an instance of permutation equivariant layers followed by potentially an invariant readout, right? So that was the foundation of geometric deep learning, right? And basically the story so far was I have some black box, right? So I have a function that has some input, right? So it can be a graph, can be an image, can be whatever you want, right? So depending on what kind of object you deal with, as the moment you can think of this object geometrically and have a way of defining some group of transformations that acts on this input, I can describe these functions but from the way that they interact with this group, right? So for example, we talked about invariance, right? So I want to make sure that this function f, no matter how I act on the input with, for example, with my group, the output should remain the same, right? And by the choice of this function and the choice of the group of transformation, you can design different architectures, right? So convolutional neural networks, we derived convolutions from first principles, right? So they come from commutativity with the shift operator, right? So I give you a grid, I give you a translation group, right? And you get automatically from this blueprint convolutional neural networks. Again, I give you a graph with a permutation group, you get graph neural networks, right? So that's the way of dealing with this symmetry. And you can do also more exotic things. So we didn't really talk about manifolds, but on the manifold, you can basically have these gauge equivariant architectures. So the local choice of coordinates is defined up to local rotations, right, on orientable Riemannian manifolds. So what is called the SO2, the special orthogonal group, rotations preserving orientations, and you get these kind of local non-Euclidean convolutions. So you can also combine different symmetries, right? So with molecules, we've seen you can, instead of, in addition to just permuting the atoms in the molecule, you can also rotate or translate the molecule itself, right? So we call this SE3 invariance. So SE standing for special Euclidean group, right? And basically it's a combination of different symmetries. And the most important application where these kind of constructions have been very important was in AlphaFold 2. So that was DeepMind's program for predicting the structure of proteins. So maybe if you're not familiar with proteins and with biochemistry in general, why people care about proteins, why they're so important, basically people sometimes call proteins the molecules of life, right? And it's kind of sounds like poetic figure of speech, but it's not. So we literally don't know any life form that is not based on proteins. So they're encoded in our DNA, and cells produce proteins for a variety of things. So for example, storing oxygen, right? So the fact that you can breathe and you don't die of suffocation because you have a special protein called hemoglobin that binds oxygen and delivers to your cells. So the fact that cell can take things in and out, right, that it can function properly, so the cellular membranes, they have this special mechanism called pumps. So these are also protein complexes. Chemical messaging, hormones, right? So I think the first protein whose structure was understood. Insulin plays part in this messaging mechanism. Any chemical reaction that happens in our body is a catalytic chemical reaction, right? So we have special proteins called enzymes that make these reactions possible, right? Otherwise, they would not be happening. Our defense against pathogens, antibodies are special types of proteins. And I can go on and on, right? So they're everywhere. So they're responsible for any important biological function that we have in life. Now, what are proteins? Basically, they are long chains, right? So biopolymers of basic building blocks called amino acids. So they stick together. And then under the influence of electrostatic forces, they fold into these complicated three-dimensional shapes. And basically, you start with a sequence of amino acids, then it folds into a three-dimensional structure, and then the structure endows the protein with some function, right? When I say function, a good metaphor is this metaphor of a key and a lock, right? So you have a key and there is only one, you have a lock and there is one key that will have the geometric configuration corresponding to the knobs inside the lock that will open it, right? So same way, proteins can recognize ideally a unique molecule that can bind it, and that's how they are selective, and that's how chemical reactions happen in our body. This is how we design drugs, right? So when we identify a protein target that is associated with some disease, we try to find a drug that fits into the surface of this protein and binds to it and then prevents it from some function, right? So it's, most of the drugs are pretty stupid stuff, right? So it's loss of function in most cases. And it was postulated already in the 70s, so Christian Anfinsen, Nobel laureate in chemistry, in his Nobel lecture in 72, he was saying that the conformation of proteins is determined by the amino acid sequence. So with some caveats, but basically this idea that you can go from sequence to structure already existed in the 70s, and there was a competition that started around that time called CASP, Critical Assessment of Structure Prediction, where basically structural biologists were trying to test their latest and greatest algorithms who can predict the structure of the protein in a better way. And it was running for years, and in 2018, a newcomer came, so that was DeepMind, that outperformed anybody else. So all the methods before were based on first principles, based on physics, right? So the best physical model of how proteins fold and how they form this three-dimensional structure. So it was this kind of ImageNet moment for structural biology, right? So when you replace handcrafted methods, right, or your best approximation of the problem with a learning-based approach that learns from data, same thing that happened with images exactly 10 years apart. The same thing happened with proteins, and yeah, as I mentioned, the Nobel Prize in Chemistry was given for AlphaFold. Now, if you look at these two breakthroughs, so they're exactly 10 years apart, right? So the ImageNet breakthrough happened in 2012, and AlphaFold 2 was published in 22, so it's exactly 10 years. It is pedagogical to look at the time that it takes from the introduction of the algorithm to the breakthrough versus the time that it takes from the introduction of the data set on which the algorithm was trained. And you will always find that data trumps algorithms. So that the time from the data set is much shorter. So this was the case in ImageNet, right? So ImageNet was introduced in 2010. The convolutional neural networks on which that were trained on this data set, maybe with a few tweaks, but that's roughly the same stuff that LeCun was doing in the 90s. So we are talking about something like 2 years versus 30 years, right? And this is true for other breakthroughs that happen in AI and machine learning. So it's interesting actually that in AlphaFold, this is probably the first time that this trend didn't happen. So the data existed forever. Maybe not in the majority of it is recent, but the structural collection that was called PDB, the protein database, started in the mid-70s. And the main algorithmic ingredients of AlphaFold were equivariant architectures that are, again, ideas are maybe older, but at least the mainstream methods are roughly from 2017-18, and transformers. So transformers is the famous paper, Attention is All You Need, from 2017, right? So we really need to look into it, into more details, what goes into AlphaFold, because also the amount of data on which it was trained, right? So if you look only on the structural data, it is tiny by any machine learning standard. It's a very large data set for biologists, but only 150,000 structures. That's it. So this is an order of magnitude less than the ImageNet on which AlexNet was trained in 2012, right? And this is a drop in the ocean compared to the commercial models like GPT. So GPT-3, so that was the last official data from OpenAI, 300 billion tokens. So the most recent models are probably trained on tens of trillions of tokens, right? So we are talking about orders of magnitude bigger data sets. And then we need really to look into it, what makes machine learning suitable and successful in a particular scientific problem, right? So how do you look at the problem? How do you choose the problem? Because you can look at in retrospect and say that protein folding was an easy problem. You just need to choose it wisely, right? So of course, it is very unfair to say because it was a difficult problem. But again, from a certain perspective, right? So if you look at it as a machine learning application, it was not that difficult problem, or at least it had the right ingredients for machine learning to be successful. And I wish I knew the answer, but you can make an educated guess, right? And I would like to make 4 educated guesses. So these are the recipes, what is needed for machine learning success in a problem, right? So I guess you ask this question, you ask yourself this question all the time, right? So you work on some important problem in science and engineering, maybe the first thing you want to try is latest and greatest machine learning architecture, but maybe before you do it, does the problem have the right ingredients, so to say, to be actually addressable by machine learning, right? So I guess the first 2 are not controversial. It's existence of large and diverse data sets and clear performance criteria. And we can argue about the other 2, which is what I call degenerate solution space and internal structure, okay? So the first one is obvious, right? So the ImageNet, which was established in 2010, we had 1,000 fine-grained classes, so not only cats and dogs, but different breeds of cats and dogs, and different everyday objects from chairs to cucumbers. 1.2 million manually annotated training images and 100,000 test images. So, and performance was evaluated as average test accuracy. So everything is very clearly defined. You can argue whether this is the right data set or whether this is the right problem, but at least there is no agreement that in some way it's meaningful, right? Same way with CASP. So it was established in '94 on data set that goes back to the 70s. The training was done on 140,000 PDB structures, and the testing was on new protein structures unknown to science. And the performance was evaluated as root mean square distance between heavy carbon atoms in the protein backbone. So again, you can argue whether this is the right criterion and what is the choice of proteins you want to test on. But again, largely the community agreed that this is the right problem and the right way of looking at it. Okay? Now, and again, diversity, of course, so PDB is criticized for lack of diversity. You can argue ad nauseum about it. So what about the other criteria? So the one is what I mentioned, the general solution space. So we already mentioned about it briefly. And if you look at images, right? So let's say images of cats and dogs. If I look at the space of all images, the cats and dogs do not occupy it uniformly, right? So somehow there is a low-dimensional subspace, some kind of low-dimensional structure, and often it's convenient to think of it as a manifold that captures somehow the degrees of freedom that we have in cats and dogs. So you don't have, for example, 1 million degrees of freedom that explains how different cats look like. Maybe it will be 10 or 20 or maybe 100, but significantly less than the dimensionality of the space, right? So basically it's low intrinsic dimensionality. And there are many reasons and many explanations why this is the case. So one explanation, for example, that natural images tend to be self-similar. So if I look at a cat, I can compose it of parts of itself. And actually this has been used in the 90s for compression algorithms. So you can, what is called fractal compression. So it was a very beautiful algorithms that start with noise and apply some kind of contraction iterated operation that hides the image inside this thing. So the same thing happens with proteins. So when you will hear typically these theoretical estimates, right? So 10 to the power of 300. So that's estimated number of proteins that might exist in nature, right? So this is a very large number. If you think of the number of atoms in the universe, it's only 10 to the power 80. If you think of individual cats and dogs, and not different species, but if you collect all the possible organisms, from cats and dogs to worms, to bacteria, to mushrooms, it will be only 10 to the power 30, right? Individual copies of different species, right? Everything that inhabits all the biomass on the Earth, only 10 to the power 30, right? So if you want to operate with more tangible numbers, so this is the national debt of the United States. It's only 10 to the power 13, right? So it's quite a big gap. But we don't, maybe now it's more, right? So it's growing every second. But we don't see all these proteins in nature, right? So we don't see all these 10 to the power 300. And the reason is that proteins are not just some random molecules, they're a result of evolution. And nature seems to be lazy and it likes to reuse existing solutions that work somewhere else, right? So, and here's an example. So this is called Tim-Barrel fold. So it is very old. So it appeared in what is called LUCA, the last universal common ancestor. So some kind of primitive organism, then all of you and all of us were still bacteria, so a single cell primitive thing, more than 3 billion years ago. We all had this kind of structure. So this is a structure that has 8 copies of the same structure. So this helix and helical structure, and it appears just as copies and pastes, and it is heavily reused. So we find it in about 10% of all enzymes across diverse species and across diverse functions. So we see it in chemical reactions in our body, or in a tomato, or in a bacterium, right? So it's everywhere, right? So it's just nature liked it and copied it because it worked. So same thing happens with in other problems as well, right? So basically this kind of self-similarity, we see it in images, we see it in proteins, we see it in text. So this is one of the common characteristics of natural things somehow, right? So that it has this degenerate solution space. So the last thing I wanted to mention is internal structure, and we see it in text. So if I give you this sentence and I mask out a word, I guess you can fill in the blanks, right? So there are probably multiple possibilities, but probably bank will be the right word. And how do you do it? You know it from the context, right? So in the first case, the context it talks about something related to a river, right? And we know that bank has the meaning of a side of a river. In the second case, it's about a financial institution that is also called a bank, right? So this is how LLMs work, right? So you take a lot of words, right? So a lot of sentences. So the training data is humongous. You mask out one of the tokens, and you try to predict it from context. So it's either the next token, right, or the predicting from words before and after. And this is possible due to what is called distributional hypothesis, that words occurring in the same context tend to have similar meanings, right? So it's not just some random stuff, right? So I cannot put a random word here. It has to be semantically and grammatically correct. So by learning this prediction task, and you learn it on a lot of data, you actually learn the meaning of the words and the grammar of the language, right? So that's why you can generate words that are correct both grammatically and semantically. So the analogy of this in proteins is multiple sequence alignment. So again, because proteins result from evolution in similar organisms, proteins that do similar function will have similar structure and will have similar parts of their amino acid sequence. So you can just align these sequences using string matching algorithms, and you can leverage these for the prediction of the structure. And multiple sequence alignment was the second important ingredient in AlphaFold. And in fact, it doesn't work well without multiple sequence alignment. So if you look at the evolution of this problem, right? So starting with the early algorithms, like what David Baker has been doing for his entire life, more or less, since the 90s, all the first principle physics-based models, so it never really worked well. So it produced some results, but it relied on models that everybody knew were not correct, right? So it was the only tractable approximation of the problem. So AlphaFold 1 that appeared first in 2018 was 3 separate machine learning models. So one was for computing distances between amino acids, one for confidence, and another model was for multiple sequence alignment. AlphaFold 2 was already a single end-to-end model. It heavily relied on geometric intuition, so they had frame-based representation of the backbone of the protein, and used the equivariant architecture, so this important part that was called the invariant point attention. So what are the next steps? So the next step in the evolution, AlphaFold 3, was a general diffusion-based transformer. So it ditched all the geometric equivariant parts, and it used extensively data augmentation, right? And actually, they were not the first. So the first to show that you don't need equivariance for good prediction of molecular structures was my own PhD student. So he just started his PhD by trying to contradict what we've been doing for the last many years. And that was his work with collaborators from Apple. And does it mean that the end of geometric and equivariant architectures, right? So we have these mathematically beautiful rainbow castle on the hill, right, where everything is nice, and we can spend 2 days talking about equivariant architectures, or we have these brute force data and compute-based solutions. So the reality is more nuanced, right? So you can talk, of course, about what is mathematically more correct, but at the end, what determines everything is hardware. And this was another lesson. So this was what Google Brain people called the hardware lottery. It's the fact that research ideas win not because they're necessarily superior to other research directions. So it's because they're better suited for available hardware. And this story appears multiple times. So Sarah Hooker in this paper, I warmly recommend to read it. She shows historical examples, including some research directions that were considered dead end and were not pursued. And then when hardware changed, they suddenly became popular. So the story of convolutional neural networks is exactly this, right? And I think I mentioned it answering one of the questions yesterday. There is nothing special about convolutions, right? So this is by far not the right, translations are not the right group in computer vision, right? So if at all, you probably are interested in perspective transformations, right? So at least the projective group, right? So something that is arguably bigger and more correctly representing the kind of transformations that three-dimensional objects undergo when we look at them through the camera lens. So why convolutions? What is so special about convolutions? So the only reason is that first DSPs and then GPUs were designed to do efficiently only one operation. So it's multiply a vector of numbers by another vector of numbers and sum them up, what is called multiply and accumulate. So the first DSPs were doing it at about 120 million times per second. So that was extremely cool technology in the 80s, right? So this is what was used for filters. And LeCun just took an architecture that already existed and made it efficient for the DSPs, and the rest is history, right? Same thing with transformers, right? So we heard today that transformers are graph neural networks. So what is so special about transformers? Why at all do you need permutation invariance, right? Which you get in graph neural networks for problems in natural language processing. In fact, you don't want it, right? And you need to introduce positional encoding that breaks this symmetry, because transformers can be implemented efficiently on the GPU, right? So the hardware lottery. So if you think of it, if I can use, again, this equestrian analogy, so we have this big multi-trillion cart of AI that is pulled by these three powerful horses. So one is compute, another one is data, and the third one is models. And they don't just run in a field in arbitrary directions. So they're in a very narrow valley that is constrained by hardware, right? So we have the hardware lottery that tells these horses where to run, right? So, and as long as we are using GPUs, and probably there is no end to it, at least in the near sight, it will be anything that can be implemented on the GPU, right? So any other ideas will probably even not be considered, because you cannot just implement them efficiently, okay? But it's interesting that we already got to the situation where the models themselves become a sort of data modality, right? So this is a picture from Hugging Face. So these are the repository of different LLMs. So each point here is a model, and you can see that different relations between them. So there are more than 1 million weights of different LLMs that are deposited there. So you can actually use the weights of the neural networks as the new data modality. So you can train neural networks that take as input other neural networks, right? So the weight space itself becomes an interesting data modality, right? And what does it have to do with all the group theory and the geometric deep learning? Because remember, so basically all these 2 days that we were talking about can be summarized in this one picture, right? So what do I do to my input, and how I design my function, right? My neural network that it respects the transformations of the input, right? So whether it's permutations, whether it's shifts, whether it's other stuff, right? But it's only half of the story, because neural networks have 2 types of inputs. So it's the input itself and the parameters, right? So the weights of the neural network. But the space of the weights also has some geometric structure, right? So the complete picture would be, we also have another group that acts on the weights, and we are interested, for example, in invariance in this space, right? So what are different configuration of weights of a neural network that are functionally equivalent, right? I would like to be able to tell, right? So this is one of the reasons, for example, why we have non-convex loss functions, right? So there are multiple solutions that produce exactly the same result. So here is an example, right? So if I have just one hidden layer, I can permute the neurons in this hidden layer and the result will not change, right? So it's just like renaming them. So I need to permute the weight matrices accordingly, of course, right? But this is the most straightforward transformation in the weight space that produces functional equivalent things. Now, take LLMs, right? So Alicia talked about it. So we have in commercial models now hundreds of billions, if not trillions, of parameters. So these are gigantic matrices of parameters that we cannot really train these kind of models, right? So we don't have the compute power that Google or Meta has. So what people do, low rank adapters, right? So you take your pre-trained model with its parameters, you assume that these parameters are frozen, and you change the parameters with a low rank matrix, right? So that looks like this, U V transpose, right? So now it's a thin matrix, so you have, instead of quadratic number of parameters, only linear number of parameters, right? So the W is frozen and the U and V are optimized. Still, it is quite heavy thing, but what you see here is that there is an ambiguity. So if I multiply U by some matrix R and V by the inverse of R, right? Any invertible matrix for this purpose, the result will be the same, right? So these things cancel out. So basically my solutions, right, in this UV representation space are defined up to general linear group, right? So the group of all invertible matrices of size R by R, right? So if I want to work with LoRa's directly, right, as this U and V representation, I need to account for this symmetry, right? And this is what we can do. So we can design an architecture that takes LoRa's as input. So it's a neural network that learns or that operates on the weight space of, in this case, of transformers, or in this particular representation, okay? And this kind of architecture can be trained significantly faster. You can fine-tune your models up to a million times faster compared to the usual techniques, okay? So back to our discussion on AlphaFold and proteins. So basically the lesson from the data lesson was that because data trumps algorithms, somehow, especially after the Nobel Prize, we all tend to think of how to design the next generation of AlphaFold, right? Again, metaphorically speaking. So what is the coolest new machine learning architecture, whether it's some new generative model that will fold the proteins better? Nobody is thinking of how to design the next PDB. And we should be thinking of the next PDB rather than the next AlphaFold. Because when you have good data, algorithms are simple. And when you don't have good data, then learning is a hard problem, right? So what is the problem with PDB? That it took only 50 years and only $50 billion to build. Nobody ever counted it. So this is an estimate, because it has never been conceived as a machine learning data set. So it was a byproduct of scientific discovery. So a PhD student made an entire PhD thesis work on some protein complex and obtained crystallographic structure of this protein, studied it, and then deposited it in a data set. And then another student did it, and then another one. And then it grew from the 70s to maybe a few thousand structures to now about 250,000, right? And again, it seems like a big data set, but it's tiny by machine learning standards, right? So the problem with biological data, and I think it's probably correct for any experimental science, is that we like to look at this picture, right? So with these horses, and we think of data that is something that goes without saying, right? So when it comes to commercial models, right, that work on text, so text is unbounded, right? We can get everything from Google. So all the output of the human civilization is accessible, whether it's text or images, right? But when it comes to experimental data, data is expensive. So the reality looks more like this. So this is our data. So basically, if we want to progress with the use of AI for science, we need to, first of all, change the way that we produce data. So we want to make sure that the data is not a byproduct of the scientific discovery, that this is the core of the scientific discovery. And it means that also we need to solve this gap of something up to 6 orders of magnitude in the cost and the time it takes to acquire this data. And this is where I believe it is important to move away from data that is designed and collected by humans for humans, and this is what we call black box data. Right? So let me try to explain what I mean by this. So it was a little bit controversial concept. So roughly people were saying either it's total nonsense or we've been doing it in the last 20 years. So I think the probably more correct description is that people have been doing it maybe without calling it this way. Right? So if you think of the first generation, but I will use again proteins as an example, but it applies to other situations as well. So first algorithms for protein structure prediction were a white box, right? So you try to code your best understanding of the physical system, first principles, right? So you write software that tries to estimate forces on different atoms in the protein molecule, right? And you run it, and it predicts the protein structure, right? And it was also tested and fine-tuned on white box data, right? So crystallographic data and later cryo-EM data, protein structures. So the big leap was with the introduction of machine learning methods, black box methods like AlphaFold. So you don't really understand what's going on, right? So you don't have an equation of a protein, but it learns something from the data and it works better because it doesn't restrict yourself to the incorrect model. So it tries to leverage the information that you have in your data. It's still trained though on white box data, on data that was collected by human scientists that human scientists can look at and understand, right? So full three-dimensional structures of proteins. I believe that the next logical step would be to move away altogether from this human interpretable white box data to what we call black box data. So it's massively scaled, cheap data where you intentionally sacrifice human interpretability of individual data points in favor of scale. Right? So it doesn't necessarily need to be non-interpretable, but it could be non-interpretable. Right? So you're allowed to give it up, the interpretability. And one example is actually from a company that I'm involved in. So it's called Vant AI. So it's a biotech company based in the US. And Vant is in the business of designing molecular glues. So as I mentioned, most of the drugs work on the principle of loss of functionality. So roughly you stick something to a protein and it loses its function. So it doesn't bind to whatever it's supposed to bind. So molecular glues work differently. So these are proteins that normally do not interact. You try to make them interact. You want to rewire the normal functioning of the cell. So basically molecular glue is a small molecule that brings two proteins together and makes them interact. So it creates a new surface that will be recognized by the other protein. And one particular mechanism that is employed that exists in our cells is the mechanism of protein degradation. So cells have natural way of destroying proteins that do not look well or do not work well. They just need to be repurposed for a particular target. So instead of drugging the target, you can mark it for degradation. So you bring it into proximity to a special enzyme called E3 ligase, and then basically the ligase attaches a special protein called ubiquitin, and then the cell recognizes it and destroys it naturally. So the problem is that it's a difficult problem. So it's a chicken and egg or a two chicken and one egg problem. So you need to fold two proteins together that normally do not form a complex. The complex is formed only in the presence of the small molecule, which you don't know ahead of time, right? So you need to co-fold the proteins and generate the small molecule at the same time, right? And the experimental data that we use here is cross-link mass spectrometry. So it's basically, these are sparse constraints. So these are molecules of certain distance that tell us that a few amino acids in the protein complex come at certain distance, right? So it's sparse contact points, but it restricts a lot the solution space, right? So it works very well across the board. So across docking, across generation. So you can see here an example of docking, basically how to predict the poses of two proteins with respect to each other. And you can see here also basically these complexes that are produced by these molecular glues that without these experimental constraints, we do not have a good way of predicting them, right? And here you can see that this information helps across the board, right? So whether it's docking or whether it's structure prediction and so on. And again, I mentioned that people have been using it quite extensively without calling these black box data. So probably the purest mathematical example is compressed sensing. So in compressed sensing, your data literally looks like noise, right? So you design it in a special way that even with mathematical guarantees, you can then recover the signal. So another example is computational photography, right? So if you look at this phone, right? So what you get from the sensors doesn't look like the final picture. So it actually has multiple sensors. So it has 3 cameras, it has depth sensor, it has a lot of different things. So computational photography fuses information from these sensors into a better picture. So there are exotic sensors like event cameras, where your image, it doesn't even look like a matrix of pixels. So it looks like a sequence of events. So you know that at this particular pixel, at this particular time with megahertz frequency, your pixel went darker or brighter. So your sensor doesn't need to be even to be a high quality thing, right? So it just needs to sense whether you're black or white, right? So whether you become darker or brighter with high frequency, right? And then there is a special reconstruction algorithm that makes it into a video. So in biological sciences, probably one of the biggest achievements of biotechnology was sequencing of human genome. It was also possible thanks to this black box paradigm, so the shotgun sequencing that breaks the genome into tiny pieces with a lot of overlaps and then stitches them together with sequence alignment algorithms. So basically it was on purpose giving up on the interpretability of individual data points in favor of scalability. Right? So that was the technology developed by Craig Venter, and that was key to completing the human genome faster and cheaper. Okay, so basically the lesson that we can learn, right, is that we need AI-first data sources. So this is what we call black box data. We need to separate data generation from human consumption and design experimental protocols that might look like noise to human, but provide massive scalable signal that is required to train the next generation of machine learning models. And again, there are many examples in the biotech domain that allow me to skip. So maybe the last few minutes, let me dedicate to maybe a more general philosophical musings about AI and where does it put us in the scientific discovery more broadly. So I like this quote, Sidney Brenner, so well, another Nobel laureate, so he was Nobel laureate in medicine. He was saying that progress in science depends on new techniques, new discoveries, and new ideas in that order. So the order is important. If you think of, again, life sciences, so the new technique that was revolutionary was the invention of the microscope, right? That allowed us to see cells. Before that, people thought of biology as some kind of magical forces that make living things, right? So for the first time, we've seen cells, and we could understood how living matter works, right? So what are new discoveries? For example, discovery of the structure of the DNA that gave us the modern field of genomics, right? So it was fundamental in the last 100 years. And new ideas, for example, theory of evolution was a new idea, again, that had profound impact on biology, right? So if you think of artificial intelligence, it probably ticks all the 3 boxes. So it's a new technique. It can lead to new discoveries, right? So you can argue that AlphaFold has produced new discoveries, and maybe at least we already are seeing baby steps, new ideas. So it's not anymore just a mechanical amplification of the brain. So it is increasingly, and again, you can argue about it to what extent it takes part in the creative discovery process. And Newton is probably always presented as the classical example of the triumph of scientific theory, right? So that this proverbial apple that fell on his head and made him think of the laws of gravity that then he formulated mathematically and confirmed experimentally. This is how science has worked in the last four centuries, right? So we always start with a hypothesis, then we use it to make predictions, and then we confirm it experimentally, and technology has been involved in all these steps. And of course, since Newton, things have changed vastly, right? So his telescope was very primitive by today's standards. Nowadays, we can even measure gravitational waves, but it has always been the case that the hypothesis generation has been the human endeavor. Call it the eureka moment or the spark of genius or whatever. It has always been the child of the human brain. And this is challenged probably for the first time ever in the history of science and the history of human civilization. And it gives us some sort of science that we don't really understand, right? So AlphaFold is probably the first example. So the first who gave it the name was Chris Anderson. So he called it the post-theory science. And I think it was nicely described in this article. So here I quote, somewhere between Newton and Zuckerberg, theory took a backseat. So much data had accumulated and computers are already so much better than us at finding relationship within it. Soon, the old scientific method of hypothesize, predict, and test would be relegated to the dustbin of history, right? So AlphaFold is a good example, right? So it's a black box method. So it produces correct predictions. So it probably ticks all the boxes of theory, but we don't have an equation of a protein, right? So we don't have a theory of protein folding. We have a black box that works, but we have no idea how, right? We don't really understand what it does. Maybe we do to some extent, but not. It's not really something that a human intuition can understand, right? And we see increasingly more such progress in science. So the old paradigm of science, right, if I were to rename it, you start with understanding, right? We start with human intuition, with the apple falling on Newton's head. Then you use this intuition to encode it in mathematical language, right? So from the falling apple, he wrote the law of gravity. And then you use this mathematical understanding to simulate, right? In his case, he made predictions about the motion of planets and then observed them through the telescope. So with complex systems like what we see in life sciences and biology, we don't have the understanding. We don't have an equation of a cell. We might never have. It's too complex. Maybe everything that was amenable to human intuition and we were able to reduce to this simplistic form that our brain can conceive and understand, maybe this already has been discovered. So we need the same way as we had the change from software 1 to software 2 to change the order. So we start with encoding. So we have a black box, we have a neural network that is trained on data. So this is our encoding of the physical or biological reality of the system that we are studying. Then we use this black box to simulate, and only then we try to understand it through mechanistic interpretability methods, whatever exists and whatever will exist in the machine learning community. Right? So different way of approaching science. So I believe that this is how it will be working, and basically this changes everything, right? Because for encoding, we don't need human interpretable data. So it can be black box data, something that makes sense only in conjunction with machine learning algorithms. So I started with this example of Faust, right? And Goethe, as you probably know, so you know him mostly as a poet, but he was also a scientist. So he was the last student of alchemists. So he studied with Spielmann in Strasbourg, and Spielmann was one of the last alchemists. So they still had a very rudimentary understanding of how chemistry works. So everything that they couldn't understand, they attributed to some semi-magical forces. So things that made inanimate matter into living things, according to alchemists, was the encheresis naturae, the hand of nature. So some kind of semi-magical force that supposedly breathes life into living matter. And of course, Goethe was very unhappy with this explanation, so that's why he puts these words and this term in the mouth of Mephistopheles. Encheresis naturae is the chemical name by which dances themselves unwittingly shame. So I think now with this hype of AI, so we risk going back to alchemy. So I think I started with the alchemy analogy from Ali Rahimi. So he was complaining about deep learning being black boxes, but here we have alchemy in the sense that we delegate all the somehow magic powers to the machine. So again, the encheresis machine instead of encheresis naturae. So it will not work. You need to develop machine learning methods together with the experimental techniques. So you need to develop new data sources and machine learning methods that can take advantage of these data sources. Only then, in my view, we will be able to make real scientific progress with these methods. So thank you for listening. I will stop here and we'll be happy to answer any questions.
You had explained about molecular simulations using DF8. But DFT doesn't scale to larger molecules and also very slow. Do you see improvement in that direction?
Yep.
Do you need improvement in that direction, and how should it come?
Well, so you replace it with genetic models. So roughly the idea of all the numerical, right? So iterative methods, simulation-based methods, is that you solve correctly the wrong problem, right? So the wrong in the sense that it's incorrect level of abstraction or too coarse an approximation. Generative models solve the right problem in a way that is sometimes correct. So you need just to make sure to discard incorrect solutions. So in the case of DFT, so we had recently a collaboration with a group of Francis Arnold at Caltech on crystal structure prediction. So organic crystals are important type of structures. So they're everywhere from electronics like OLED displays to even formulation of drugs, right? So when you actually take a pill, so it's a crystal. So the way that the molecules are packaged there makes a lot of a big impact on how they metabolize in the body. So long story short, it's a difficult problem. So it's even more difficult than protein structure prediction because you don't have the evolutionary history. So basically we're using a generative model instead of the simulation, and the baseline is a DFT. So it works comparably in terms of accuracy to the DFT, but orders of magnitude faster.
Generative model is your genetic model.
Yeah, it's a genetic model.
Okay. So like, what are the how do you structure the model? Like, let's say we talk about.
So you need to train it on data. So we use basically you need examples of crystals. So we go basically it's ab initio method. So you go from the molecule, individual molecule to the crystal structure. So it's actually an all-atom non-equivariant architecture that we use for scalability purposes, and the equivariance is introduced in the software.
So in the last few slides, you explained about the black box data. So which type of molecular applications do you expect to use them, or expect others to use them? And what does what should that data look like? It's like what type?
Well,
what type of properties or like?
Yeah, so specific data depends really on the applications, but you can see these methods used across all the stages, for example, of drug discovery and development. So here we identified some common properties that are important in the design of the black box data protocols. Like, for example, you can sacrifice resolution. You need amplifiable signal. So that the signal, the SNR can be very low, but at least you need to be able to amplify the signal. You can use pre-training. So often you can pre-train on data that is not directly relevant to your problem, but it still contains useful information. So for example, protein language models, right? So even though your downstream problem can be very different, you can pre-train on, for example, on sequence data. You don't want to lock yourself in for a particular hypothesis. You can use proxies, right? So readouts that are not necessarily don't contain directly relevant information, but related information. No cleaning of the data. So sometimes absence of data is also informative. So there was recent work, for example, about some missing NMR peaks in proteins that actually contain important information. Yeah. So.
But many of these seems like just corrupted data, like low quality of data. So how do you design the model?
Yeah. So the quality. So it's again. So it's human intuition, right? So we always hear that we need to prioritize quality over quantity, right? So that's human brain. That's how it works. So we can look at a few examples, but they need to be high quality examples. In machine learning, it's the other way around. So quantity is quality. So if you think of, again, of commercial models, so they're trained on a huge amount of data that is very noisy. You just need maybe a small amount of high quality data and some kind of refinement procedure. So what worked well, for example, for GPT was reinforcement learning from human feedback. So some sort of lab in the loop might work for experimental data.
Thank you.
More questions? Yep.
Thank you. So I really like that you mentioned and so current paradigms are focused on black box models, right? But you were mentioning that we should think about black box data. So has there been works around that? Like have people thought of that, or like is this completely new thing that you were mentioning?
No, I don't think it's new. Well, maybe they don't call it black box data, but it has been around, in particular in biotech applications for a while. So all sorts of approaches from pulled screens to proxy readouts. So there have been many techniques. Maybe they're not completely black box data, but the idea. So I know that black box is a kind of bad term in computer science, but here the defining feature is that you are willing to trade off specific interpretability of individual data points for scale. The data can still be interpretable, maybe less interpretable, maybe it is more noisy, and it's therefore a continuum spectrum, right? So it's not black and white.
Sorry, like what were you mentioning? Those techniques in biology?
There are many. So, for example, DNA encoded libraries, right? So they allow you to screen trillions of candidate molecules, binders for. So you attach basically DNA barcodes to individual molecules. So they have their shortcomings, but this is a widely used technique, and there are multi-billion companies like in vitro that are based around it, or cell painting, right? So this is what, for example, a company like Recursion is based on. So it's also a multi-billion company.
Thank you.
Questions? Well, I guess that's it. So thank you very much.